StatQuest! 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 Hello, and welcome to StatQuest. This time, we're going to talk about standard errors, and we're also going to have a bootstrapping bonus. We'll start by talking about error bars, which are very closely related to standard errors. For example, you might collect measurements from 3 samples labeled A, B, and C, and plot them on a scatter plot, just like we see here. You could then calculate the means for the 3 data sets, and we've illustrated those here with 3 green horizontal bars approximately halfway up the clusters of data points. After that, we could calculate the standard deviations and add those to the graph, and we've shown those here with red error bars. In manuscripts and presentations, people often don't display the original data, but instead just show the mean and the standard deviation in what's called a dynamite plot, because each column in the plot looks like it's the igniter for a stick of dynamite. There are 3 common types of error bars. The first type are standard deviations, which we just saw, and I'm sure you're all familiar with. These tell you how the data are distributed around the mean. Big standard deviations tell you that some of the data points were pretty far from the mean. In most cases, you want to use standard deviations in your graphs since it tells us about your data, the data points that you collected yourself. The second type of error bar comes from standard errors. These tell you how the mean is distributed, not just the data, but the means, which sounds crazy, but it'll become clear once I draw some pictures. The third common type of error bar are confidence intervals, and these are related to standard errors. Confidence intervals will be explained more in a future StatQuest. Since this StatQuest is all about standard errors, that's what we're going to talk about. Let's start by considering a normal distribution. In this case, we can imagine that we weighed a lot of mice and plotted the distribution of differences from the mean. The y-axis is the proportion of the mice that we weighed, and the x-axis is the difference from the mean. Most of the mice had weights close to the average. A few of the mice weighed much less than the average mouse, and a few other mice weighed much more than the average mouse. Usually you can't afford to measure the weight of all the mice, so you just take a sample. In this example, we'll just assume we took 5 measurements from the population rather than measuring all the mice. Since most of the mice have weights close to the average, most of our samples are going to be close to 0. Now, just like we always do, we can calculate the mean and standard deviation from our sample. In this case, the mean of our sample is minus 0.2 and the standard deviation is 1.923. And we can plot the mean and standard deviation on our graph as the mean plus or minus the standard deviation around the mean. And for all you StatQuesters out there, here's a rule of thumb. Remember that one standard deviation on each side of the mean is supposed to cover about 68% of the data. 2 standard deviations on each side of the mean is supposed to cover about 95% of the data. This will come in handy later. The mean is now a lighter color because we're going to take additional samples and overlay additional means and standard deviations on this same graph. Here, we've taken another 5 measurements, and from those 5 measurements, we've calculated the mean and the standard deviation. And here we've plotted that mean plus or minus 1 standard deviation on each side. And now we take another 5 measurements. This is the first sample where one of the measurements is relatively extreme. However, that one measurement doesn't sway the mean that far from 0. That is to say, the means are relatively close to each other compared to the raw data. This is because, for a mean to be far from the middle, most, if not all of the raw data points would have to be in a single cluster that is far away from the middle. For example, the sample of purple points all form a cluster that are far from the middle. This could happen, but very rarely. What's much more likely is to have a sample where most of the points are close to 0 and only 1 or 2 are far away. So far, we've shown that you can calculate the standard deviations for each sample. But now that we have 3 means, we can also calculate the standard deviation of those means. Because one standard deviation will cover 68% of the values, and 2 will cover 95% of the values, the standard deviation of the means won't be as wide as the standard deviations of the data. Here, we've plotted the mean of the means, plus or minus 1 standard deviation of the means. Notice that this standard deviation is much smaller than the standard deviations we got from the individual samples. The standard deviation of the mean is called the standard error of the mean, or more simply, the standard error. The standard error gives us a sense of how much variation we can expect in our means if we took a bunch of independent 5-measurement samples. So to review, this is how we calculate the standard error of the mean. First, you take a bunch of samples, each with the same number of measurements, or n. In this case, n equals 5. The second step is to calculate the mean for each sample. Here we've calculated the mean and standard deviation for each sample, but for the standard error, all we need to do is calculate the mean. Once we've calculated the means for each sample, we can calculate the standard deviation of the means. In this case, the standard error equals 0.86. Here, we notice that the standard error is much less than the standard deviations because the means aren't as widely dispersed as the raw data. We've shown how to calculate the standard error of the mean, but there are other standard errors. For example, we can also take the standard deviation of the standard deviations. This is called the standard error of the standard deviations, which I guess is to avoid a tongue twister. It tells us how the standard deviations of multiple samples are dispersed. You can calculate the standard deviation of any statistic, for example the median, the mode, percentiles, or anything that you can calculate for multiple samples. You just calculate the standard deviation, and then you have the standard error of that. So if we calculated many medians, we could calculate the standard deviation of those medians, and we'd have the standard error of those medians. To summarize everything we've talked about so far, know that the standard error is just the standard deviation of multiple means taken from the same population. So if there's a population and we can take a bunch of different samples from it, all we have to do to get the standard error is to calculate the standard deviation of the means of each sample. Well, at this point, you might be wondering if we can calculate standard errors without spending a lot of time and money on doing the same experiment a bunch of times. The good news is the answer is yes. In rare cases, there is a formula you can use to estimate it. The standard error of the mean is 1. The formula for that is very simple. It's just the standard deviation divided by the square root of the sample size. However, there aren't many other cases. The good news, again, is that we can use something called bootstrapping for everything else. Every time we don't have a simple formula, we can bootstrap it. The nice thing about bootstrapping is it's very simple conceptually, and it's easy to make a computer do this work. Here's a bootstrapping example. Just like before, we have an experiment where we took 5 measurements. As an aside, usually for bootstrapping, it's good to have 10 or more measurements in a single experiment. Now, we bootstrap our data with the following steps. First, we pick a random measurement from the sample that we just took. This random measurement isn't a new measurement that we haven't taken before. It's not a new number that we haven't seen. It's part of the sample that we already have. Now we just write that value down. In this case, it's 1.43. In step 3, we just go back to step 1 and pick a new random measurement and write that value down, and we do that 5 times. Our second measurement is minus 1.38. The third measurement is minus 3.11. Our fourth measurement is 1.43. We've already picked that measurement before, but that's okay. When you're bootstrapping, you just pick 5 measurements from your sample, and it doesn't matter if you've picked the same one before. Our last measurement is minus 0.10. Step 4 in bootstrapping is to calculate the mean, median, mode, or whatever the statistic it is we're interested in understanding the standard error of, and we calculate that with our sample. In this case, we're interested in the standard error of the mean, so all we do is calculate the mean from our new bootstrap sample. The fifth step is to go all the way back to the beginning, step 1, and repeat that until you have a lot of means or medians or whatever you're interested in calculating the standard error of. The sixth and final step in the bootstrapping procedure is to simply calculate the standard deviation of all the means that we generated in steps 1 through 5. That's all there is to it. In this case, we calculated the standard error of the mean, and we've plotted it as a black line in the graph. So if there's no fancy formula to help us calculate the standard error, we can do it ourselves from scratch. We can just use bootstrapping and get the job done. And that's it. In this StatQuest, we learned that the standard error is a measure of how we might expect the means from many different samples to vary from one sample to another. We also learned that if we don't have a fancy formula for calculating the standard error, we can do it ourselves using bootstrapping. Okay, so tune in next time and we'll talk about how to use bootstrapping to calculate confidence intervals, and that's when things get really cool.